Okay, well, welcome back, and here's the second part of this anti-differentiation series of videos, and we're going to talk about general versus particular solutions. So in this video, we're going to really focus on dealing with the plus c. You know how to integrate now, and the procedure for polynomials is fairly simple, so hopefully you can follow that through. So here's an example, and our example is here. And it's the integral of x squared dx is x cubed. We raise the power by 1 and we divide by the new power, that 3, but we have a plus c. So if there's a plus c, it means that you have determined the general solution. And in a lot of cases, this is perfectly fine. But there is sometimes more information given and a higher expectation. So if we know one particular coordinate, then we can determine what's called the particular solution. Now, as you read a variety of different textbooks, there's some slightly different names for general and particular, but they're the ones I'm going to go with. So let's have a look at this example, but with a little bit more context, i.e., if y equals the integral of x squared dx, and it passes through x equals 1 and y equals 3, then we want to determine the function y, but the particular solution. So let's have a look at that. We know that y equals a third x cubed plus c. But we also know that when x equals 1, y equals 3. So what I'm going to do is substitute 1 and 3 in. 3 in for y, and 1 in for x, plus c. And this becomes 3, and you might be able to do this quicker, but I'll just take my time. Evaluate that first term on the right-hand side. I'm going to subtract a third from both sides, and that gives me 2 and 2/3 equals c, which leaves me with my new function, y is equal to 1/3 x cubed plus 2 and 2/3. So what I have is a general solution, but then because of a known set of information, I have a particular solution. Now let's go back to the Desmos that I had set up from the last lesson, and you'll see here that if I know a particular point, then there is only one function that can go through it. So whilst I've got a sliding a, I've got a whole number, an infinite number of possible solutions to an integration. If you then tell me it goes through this particular point, 1, 3, well, there's only one function that goes through 1, 3, and it's this one about there. So probably where a is 2. And that one goes through 1, 3. And you could solve that in that integration process, but there is only one case. So just keep that in mind. That's a really nice visual way of seeing why this works, why we get a particular solution here. So just moving forward, example 2 and example 3, and then we'll finish this off. So let's run through these examples. In example 2, dy dx equals 10x to the power 4 plus 3x squared, and it passes through the coordinate 1, 4. So this is a pretty standard question. You'll see it looking like this a lot. Determine the particular solution. So the particular solution, y first of all equals the integral of 10x to the power 4 plus 3x squared with respect to x, and we know that this is equal to 10x to the power 5 over 5 plus 3x to the power 3 over 3 plus c. I'll just create a little bit more space here, and of course that gives us, when simplified, 2x to the power 5 plus not even 3 anymore, x cubed plus c. And so the particular solution is when x equals 1, y equals 4. And so we get this. Y is equal to 2x to the power of 5, but y equals 4, my apologies. 2 times 1 to the power of 5 plus 1 to the power of 3 plus c. Now evaluate my substituted terms. I get 2 plus 1 plus c, and 2 plus 1 is 3. Subtract 3, I get c equals 1, and therefore y is equal to 2x to the power of 5 plus x cubed plus 1. And that's my particular solution. And example 3, which is a complex familiar, you're told that dy dx, which is the rate of change function, equals 7x cubed plus x plus k, and has a turning point at 3, 2. Determine the original function y. Now this is what's going to happen in the math methods external exam and even the internals, is at times you're going to be drawn back to knowledge that you have previously learnt. So we have to now hark back to that knowledge we previously learnt. And in this case, it is, what is the effect of the concept of a turning point? And that effect is that at this point here, in particular, when x equals 3, dy dx will equal 0, not 1, so 0. So we know, first of all, when x equals 3, dy dx equals 0. But we also know this coordinate is really rich in information. We also know that when x equals 3, y equals 2. So we have two pieces of information from one coordinate. It's telling us that those two different things. But we're going to use this first one to evaluate the value of k, and then we're going to integrate, and then we'll use the second piece of information to evaluate the value of c. So at x equals 3, dy dx equals 0, giving me 0 is equal to 7 times 3 cubed plus 3 plus k. 3 cubed is 27, and 27 times 7 is equal to 189. So I get 0 equals 189 plus 3 plus k, leaving me to k equals negative 192. So I've got k equals negative 192, and therefore dy dx is equal to 7x cubed plus x minus 192. And so my second step is to integrate. Y is equal to the integral of 7x cubed plus x minus 192 dx. And of course this is equal to 7x to the power of 4 over 4 plus x to the power of 2 over 2 minus 192x. So we integrate that. And then plus c. That's our second stage. Our third stage is to evaluate the value of c. At x equals 3, y equals 2, which gives us 2 is equal to 7 times 3 to the power of 4 over 4 plus 3 squared over 2 minus 192 times 3 plus c. And so I'll just evaluate that quickly, and that is 7 times 81 divided by 4 plus 9 divided by 2 minus 192 times 3, and that comes out at negative 429 3/4. So 2 is equal to negative 149 3/4 plus c, which means that c is equal to 151 3/4. And so therefore we have y is equal to 7x to the power of 4 over 4 plus x squared over 2 minus 192x, and then plus 151 3/4. And of course, here we have our week 1 resources, exercise 9a, and some of the content detail that hopefully by the end of this you'll know how to do. But that was a nice little complex for me question as well, to give you a bit of a taste of that situation. All the best.